In this video, we revisit systems of linear equations and solving them using inverses. So we should recall that a system of equations can have one unique solution, infinitely many solutions, or no solutions. We saw this back in chapter 7, and then we revisited it in section 8.1 as well. Here, phrasing this in terms of inverses, what we actually have is the following, that if A is an invertible matrix, then the system of equations represented by AX equals B, we saw this before, so X is that like column vector of the unknowns. It has a unique solution given by X equals A inverse B. And that makes sense because, again, X and B are both column vectors, okay? And they would be column vectors of the same size, so A and A inverse being the right size would also be able to apply to both sides. Now that's assuming that if A inverse exists, namely we also have the key insight that if A inverse does not exist, namely A is not invertible, then AX equals B has either no solution or it would have to have infinitely many solutions. So for example, let's go ahead and use an inverse matrix to solve the following, okay? Here in this example, I'm going to just go ahead and write out what the matrix is, and then find its inverse. So namely, we know we can rewrite this as this side is AX, and this would be B. Namely, what we have here is the following, and X would be what? X would be X, Y, Z, that column matrix. So in other words, if we write that out, what we have here is A would be 1, 1, 1. So I'll go ahead and write out the middle row first because it's going to be the longest. 0.06, 0.075, 0.095. And here we would have a 1, a 1, and a 1. Here we would also have a 1, a 0, and a 1. Sorry, that should be a 0. And a 2, sorry. 0 and a 2. And doing so, then we'd have XYZ here, right? XYZ. So this is our A, this is our X. And then we have our B, which is 10,730 and 0. Doing so, we end up with, and so this would be B. Here, we know then that we can solve this by writing it as X, A inverse times B. So X equals A inverse times B. Here, A inverse is going to be, and we're not actually calculating it out, but if you actually go through and calculate it out, you'll end up with negative 21.5 as the middle entry, 15, 7.5, negative 100, 300, negative 200, 3.5, negative 1.5, and a negative 2. So if you go through and you multiply that, right, multiplying that by B, what you end up with is, so multiplying this by that, right, going through and multiplying that through, you would end up with the solution X is equal to 4,000, Y is equal to 4,000, and Z is equal to 2,000. Okay, so again, that's X, that's Y, and that's Z. And you could always check that as well. Now it's your turn to try an example, so go ahead and use the inverse matrix to solve out the following system. Here you'll need to calculate the inverse, so I will as well. On the count of 3, I will reveal the solution. 1, 2, 3. So here we have AX equals B. going through all of the row operations and stuff. It gets a little bit complicated through here, but I've tried to show each of the things that I did, so you should be able to figure it out. And when you go through, you end up with the inverse: -1, 1, 0, -1, 0, 1, 6, -2, -3. That is, we can solve for x by doing A inverse times B. Doing that matrix product, you end up with 2, -1, -2. So x is 2, y is -1, and z is -2. For more practice in using the inverse, finding an inverse matrix to solve a system, be sure to see the textbook pages 574 and 575. In our next video, we're going to switch gears and start talking more about determinants.